Hey guys, today we're going to study molecular polarity. We have talked about polar and nonpolar bonds already, but this is different. We're going to use different logic for this lesson. We're going to reuse the terms nonpolar and polar, but instead of talking about nonpolar bonds or polar bonds, we'll talk about their molecules. We'll need charge distribution to help us with that. Please copy down this homework assignment on a separate page that you'll put under classwork in your binder. Here's our aim, what's a polar molecule? And your do now is here. You can just make sketches of these shapes. You don't need to go crazy on those. All right, nonpolar molecules. So to be a nonpolar molecule, you need to be symmetrical. And we, of course, would judge symmetry based on the way the molecule looks, and that's why Lewis dot structures for molecules can come in handy. I have included here a organizer that includes difluorine, which maybe you would just call fluorine, carbon tetrachloride, or CCl4, and carbon dioxide, CO2. I'm going to put in the dot structures now, and then we can talk about their polarities. So here they are, difluorine, just make sure that it has one bond in between. The carbon tetrachloride, 4 single bonds. Don't forget your non-bonding electrons. And carbon dioxide is a little bit different. It has 2 sets of double bonds. And here's my non-bonding electrons. So in terms of polarity, remember, a polar molecule would be not symmetrical, and a nonpolar molecule, as it says up here, is going to be symmetrical. So that's why for each of these 3 molecules, they're all symmetrical, and therefore they're all nonpolar. So I was careful to, instead of just say nonpolar, which could get you confused between nonpolar molecules and nonpolar bonds, I am careful to write nonpolar molecule here. Because, I'm not really saying anything about the bonds right now. For instance, I can say something. For instance, right here, between this carbon and this chlorine, this bond would be a polar bond because it's 2 different nonmetals. But overall, the molecule is symmetrical, so it's a nonpolar molecule that contains polar bonds. And lastly, down here at the bottom, what class of molecule will always be considered nonpolar? Think diatomic molecules, such as, difluorine, which was the first molecule on this slide. This kind of molecule is always going to be symmetrical because it only has 2 atoms, and they're the same. And because they'll always be symmetrical, they will also always be considered nonpolar molecules. So polar molecules. In order to be considered a polar molecule, you need to have asymmetry. So just like on the last slide, I'm going to toss in some Lewis dot structures for water, hydrogen chloride, and ammonia. You'll see them here, and then what I want you to do is think about what their polarity would be based on the structures. Alright, so I'll just zoom in a little bit. Here's my water molecule, and the red dots are the 6 valence electrons that belong to oxygen, and I did put them in with the correct Lewis dot structure order. Here's my HCl. I guess calling attention to these 6 non-bonding electrons, which you shouldn't forget. And then lastly, down here we have our ammonia molecule with nitrogen as the central atom, and its 5 valence electrons in red. So I'm going to zoom back out. And one thing that all of these 3 molecules have in common is that they don't have symmetry. So since they don't have symmetry, we actually would say that these are all 3 polar molecules. And so yeah, they're all polar molecules. In case you were wondering, on the last slide, there is a possibility that a molecule could be nonpolar, but its bonds are polar. In this slide, you won't see that interesting opposite terms thing. All polar molecules contain polar bonds. So I don't know if that's worth memorizing, but all polar molecules will have polar bonds. Down here, last question, is I2 a polar molecule? I'm going to rewrite that properly. And since I2 would definitely be symmetrical, it's going to look something like this. Its symmetry is going to make it a nonpolar molecule. So no, it is not polar, because it's nonpolar, because it's symmetrical. All right, so there is this other way of describing polarity, and the Regents will do it from time to time. They'll call it charge distribution. So what you need to know is that nonpolar molecules are said to have an equal distribution of charge. So it shows up a lot in short answers. They'll say, explain in terms of charge distribution why such and such molecule is nonpolar, and you would just need to say that it has an even distribution of charge. On the other hand, polar molecules are going to have an unequal distribution of charge, so you could explain it that way as well. These charges that they're talking about are definitely electrons, and what would affect the distribution of charge would be the electronegativities of the atoms in the molecule. So generally, the most electronegative atom is going to draw the electrons closest to itself, and that's going to result in an unequal distribution of charge. I'll show you a couple of examples of that. Now I'll do methane and hydrogen fluoride. I'm going to put in their dot structures. So here they are. I'm going to zoom in on methane because I actually want to sketch the electron cloud here, and I want to show you where some of the symmetry and asymmetry may come from. Okay, so carbon is the more electronegative element. I'm going to use this funny symbol for the first time with you guys. This is a lowercase d in the Greek alphabet. It kind of looks like a funny S in the English alphabet, which is cool because it stands, in chemistry, it stands for the word slightly. So whenever you see a funny little Greek letter D, that's slightly. But in any case, the carbon is going to be slightly negative because it's more electronegative than hydrogen, and the hydrogens would be slightly positive. And down here in the second example, the fluorine would be slightly negative because it is more electronegative than hydrogen. So slightly negative on the fluorine end, slightly positive on the hydrogen end, and each one of these hydrogens are going to be slightly positive. The one that's more negative, the slightly negative one, that's going to get more electrons more of the time. So the electron cloud is going to sort of be more, it's going to bulge more around the carbon. I'm doing a really terrible job of this. And it'll be smaller around the hydrogens, but the carbon's share of electrons will be more. So this is my sketch of the electron cloud, and I'm trying to show a bulging around the carbon atom. And for the fluorine side, that's going to get more electrons over here. So I'll do a much larger electron cloud around fluorine than hydrogen, because its slight negativity is going to draw the electrons to its side more often. So I'll zoom back out, and we need to just talk about the charge distribution. So around the methane molecule, you'll actually notice that that electron cloud is evenly distributed. So the charges are evenly distributed. And around the HF molecule, you'll notice that the charges are unevenly distributed. So both of these examples that I just wrote in, even distribution of charge, unequal distribution of charge, those are both great examples of things you could say for a short answer question that asks you to explain in terms of distribution of charge. All right, so on this slide, I'm just going to compare the idea of polar bonds, which we've done before, versus polar molecules, which we're new to today. And I'm really, on this slide, I'm just trying to save your test grades because polar bonds and polar molecules are so easy to confuse, and they're both on the same test, so I want to try to avoid confusion there. Here's what I will note. Although a molecule may contain polar bonds, it does not necessarily follow that the molecule itself is polar. I'll show you examples of what I mean by this, but it's worth writing down. What must be true for a bond to be polar is that it must be between two different nonmetal elements. For example, HBr. The bond right here between the H and the Br would have to be polar because Br and H are different elements, and therefore they have different electronegativities, and their electronegativity difference would not be zero. So electronegativity diff is not zero. And if the electronegativity difference is not zero, then that's a polar bond. Now all of the following molecules in the graphic organizer below do contain polar bonds. And that's pretty easy to see because you'll always see the bond between two different nonmetals like carbon-oxygen, carbon-chlorine, oxygen-hydrogen, hydrogen-chloride, and nitrogen-hydrogen. So as I was saying, all of the molecules below do contain polar bonds. And you could say it's because it's between two different nonmetal elements, or you could explain that in terms of their differing electronegativities. But are the molecules themselves polar? Don't say yes just yet, because I already warned you up here, just because they contain polar bonds doesn't mean the molecule is polar. I split it into two different sides, this organizer. I have symmetrical ones on the left, and I have the asymmetrical ones on the right. So on the left, symmetrical ones, I just want you to say down here at the very bottom row if you would say that the molecule is polar or if you would say the molecule is nonpolar. And pause the video, and when you come back, I'll have the answers. I'm not sure if you guessed it, but on the left, the two that were already classified as being symmetrical molecules are definitely also going to be nonpolar molecules. There's really no difference in these terms, symmetrical molecule and nonpolar molecule. And then over here on the right, the ones that had already been termed asymmetrical molecules, not surprisingly, should also be considered polar molecules. So these guys, they all can have polar bonds, polar bond, polar bond, polar bond, and then I have three polar bonds here. And the molecules themselves are also considered polar as a whole due to their asymmetry. And on the left, I've got plenty of polar bonds. I've got a double polar bond, but the molecule itself is symmetrical and so nonpolar. Same thing here, polar bond, polar bond, polar bond, polar bond, but that molecule is nonpolar. All right, so you guys made it to the pair up. Copy down these questions underneath the do now questions and the homework assignment, and add in this summary. And once you have that down on your classwork and you have your notes for today, you're all set. Thanks for watching.